One of the most important applications of implicit differentiation is to help us find the derivatives of inverse functions. We'll talk more about inverse functions in a later lesson, but today I want to show you how we can use implicit differentiation to find the derivative of the inverse sine function. By the way, you also see this written as arcsine. They mean the same thing. If we take the sine of this function, we get sine y equals x. We now have an implicit equation. What's the first step in solving these types of problems? We need to differentiate both sides with respect to x. On the left side, we need to use the chain rule because we have variables that disagree. We need to take the derivative with respect to x, but our variable here is y. The derivative of sine is cosine, and we need to multiply that by the derivative of the inside, dy dx. This is one of the most common mistakes students make on the AP exam when they're solving problems related to implicit differentiation. They forget to use the chain rule and leave out the dy dx. Over to the right side, the derivative of x with respect to x is just 1. Now let's isolate dy by dx. In our previous lessons, like the ones with the ellipse and the lemniscate, we stopped here and just plugged in x and y values. And that's because we just wanted a numerical slope at a specific point that was given. So in those cases, it's okay to leave your derivative in this implicit form, where you have both x's and y's mixed up. And of all the released FRQs that I've seen, that's all they ask you to do for implicit curves. But generally, when it's not too messy, you want to rewrite these derivatives in terms of x explicitly, especially when you have trig functions because they often simplify into cleaner expressions. Our original question was, what is d by dx of sine inverse of x? And so far we have the following answer, 1 over cosine y. And when we substitute sine inverse x into y, we get 1 over cosine of sine inverse x. Now this is a correct answer, but these simplify into much cleaner expressions, and that's a skill you'll have to develop just by doing some problems. One way we can clean this up is to use the Pythagorean identity. Solving for cosine gives us the square root of 1 minus sine squared. And since we started with sine y equals x, then sine squared y is just x squared. Another way to illustrate this is using a right triangle. When we write sine y equals x, y here denotes the angle. And sine is the opposite leg over hypotenuse. So the opposite leg here is x and the hypotenuse is 1 for sine y equals x. That makes this adjacent leg the square root of 1 minus x squared. And since cosine is the adjacent over hypotenuse, cosine of the angle y here is the square root of 1 minus x squared over 1, or the square root of 1 minus x squared. Plug that back into our derivative, and now we have the explicit form. You're going to end up memorizing these derivatives of inverse trig functions, but we'll get to them in a later lesson. Now finally, you got to be careful about the range these equations apply to, which is another common pitfall for students. You want to be able to draw graphs and know where the stuff makes sense. You can see that the domain for x is between negative and positive 1. Here's what the graph of sine y equals x looks like. It's just a sine curve tilted on the side. If we restrict y values to quadrants 1 and 4, between negative pi over 2 and pi over 2, cosine is always positive. The range of the function includes the endpoints, but the range of the derivative does not. Because look, as cosine reaches these endpoints, negative pi over 2 and pi over 2, the tangent lines reach vertical, which is an undefined slope. Now you try one. Find the derivative of the inverse tangent function, also known as arctan. Applying tangent to both sides, we get tan y is equal to x. differentiate both sides with respect to x. Hopefully you memorize the derivative of your trig functions. The derivative of tangent is secant squared. Now, if you forget these, you can just rewrite tangent as sine over cosine and then use the quotient rule, but that'll take you much longer. Now, secant squared is the same thing as 1 over cosine squared. And don't forget to multiply by the derivative of the inside function. Instead of dy dx, this time I use prime notation. Over to the right, the derivative of x is 1. Solving for y prime, we get y prime equals cosine squared y. Here's our original implicit equation, tan y equals x. And I'm going to encode that into a right triangle. Again, y here denotes the angle, and tangent is the ratio of the opposite leg over the adjacent. So we'll make the opposite leg x and the adjacent 1. That means the hypotenuse is the square root of 1 plus x squared. Now what's the cosine of y? Well, cosine is adjacent over hypotenuse. So cosine y is 1 over the square root of 1 plus x squared. Which means cosine squared y is 1 over 1 plus x squared. Therefore, d by dx of tan inverse x is equal to 1 over 1 plus x squared. So to recap, we used implicit differentiation to find the derivatives of sine y equals x and tan y equals x. And then we apply the Pythagorean identity to convert that implicit result into an explicit formula.